Hi, I'm Marina Hashish, PhD candidate in the Laboratory for Astrophysics at the Leiden Observatory, and I currently work on the preparation of infrared spectroscopy dataset for complex organic molecules in ISOs. Here, I'm presenting the work focusing on methylamine molecule. The composition of interstellar ice has been revealed by infrared astronomical observations in the past decades, and to know the composition of these frozen materials are important, since interstellar ices are considered to be a formation site and reservoir of complex organic molecules in space. But so far, only a handful of molecules has been securely detected, and from these, the most complex one is methanol. In the near future, this scenario may change. With James Webb observations of ices, weaker and new features of more complex molecules may be revealed. But for correctly assigning these features, laboratory data is needed. So for supporting James Webb observations of ices, a series of laboratory ice spectroscopy work has been carried out. These works focus on the characterization of the mid-infrared spectra of frozen cones in simulated interstellar conditions, and a number of molecules have been already studied. And the most recent molecule in this series is methylamine. For the measurements, icing containing methylamine, water, methane, and ammonia were deposited at 15K and warm at higher temperatures. The infrared spectra of the ices were monitoring, allowing to characterize changes due to ice composition and temperature. We also perform laser interference measurements to derive the refractive index, ice thickness, and bed strengths of methylamine features, and the results of the studies were recently published. All the data is available through the Leiden Ice database, and if you want to know more about the database, please check out Will Rocha's poster. Our data were compared to the spectra of young stellar objects taken with Spitzer in the 5.9 up to 80 micrometer regions. And the analyzed ISOs have strong absorption features in this region that coincide with the Na2 deformation mode and the Ca3 deformation mode of methylamine. Nevertheless, no constraints on the methylamine abundance could be derived, as these features result from a blend of many species. We also compared our data with isospectra acquired with ground-based telescope in the 3 to 4 micrometer regions. And although other molecular species absorb in these regions, for example, hydrocarbons, tighter constraints on the methylamine abundance could be derived. So we used the band assigned to the CHN symmetric stretch mode around the 3.47 microns, and we determined upper limit for methylamine as being less than 4% in relation to solid water. Here I left you with a summary of our work and some future perspectives, and if you want to know more, please check out the references.